There is something going on out there that nobody saw coming. And when we finally caught it, it broke just about everything we thought we understood. Not a little bit, not around the edges, right in the middle where it hurts the most. Here is the setup. You fire a cannonball into the air. It goes up, it slows down, gravity pulls it back, it comes down. That is the story. Energy fights against gravity. Gravity wins. Everything falls back together. Now imagine the cannonball is a galaxy, and the air is all of space, and the cannon shot was the Big Bang. You would expect the same story. Everything flying apart, slowing down, gravity doing its inevitable work, pulling it all back, maybe even collapsing in on itself someday in what some people call a big crunch. That was the reasonable bet. That was the boring, sensible, satisfying answer. But in 1998, two separate teams of astronomers were doing something extraordinarily careful. They were measuring how fast distant galaxies are moving away from us. Not nearby galaxies, old, faraway ones, which means they are also old light, ancient light, photons that left their source billions of years ago. And when you look that far back, you are looking at the universe when it was younger. So if you compare those old galaxies with nearby ones, you can read the history of expansion like rings in a tree. You can see whether the universe was faster then or slower then, and watch how the rate changed over time. And what they found was not a slowing down. It was the opposite. The universe is not decelerating. It is accelerating. It is expanding faster and faster with time, which is, in the language of physics, absolutely bonkers. Think about that cannonball again. You fire it into the sky. It goes up, you wait, and instead of slowing down and coming back, it speeds up and keeps speeding up. That would require something pushing on it from the outside, some invisible force, constantly adding energy to the system, something working against gravity in a fundamental way, not just locally, but everywhere, all at once, in every direction simultaneously. We do not have a name for what that something is that captures any real physical insight. We have a placeholder. We call it dark energy. But calling it dark energy is a bit like saying your car broke down because of a mechanical problem. It is technically not wrong, but it does not tell you what is actually happening under the hood. Now let me tell you how we actually measure this, because the method is beautiful and worth understanding. There is a type of stellar explosion called a type I supernova. These are not just any explosions. They are remarkably consistent. When a particular kind of dead star, a white dwarf, accumulates enough mass from a companion star to hit a very specific threshold, it ignites in a thermonuclear runaway that is almost the same every single time. The peak brightness is nearly identical across the universe. This makes them what astronomers call standard candles. You know how bright they actually are, so you can calculate how far away they are based on how dim they look. It is like knowing that every lighthouse in the world runs a 100-watt bulb. If one looks faint, it is far away. If it looks bright, it is close. The math is simple. And then you also measure the redshift. When a galaxy is moving away from you, the light it emits gets stretched. The wavelength gets longer. It shifts toward the red end of the spectrum. The faster the recession, the bigger the redshift. So you have distance from the brightness, and you have velocity from the redshift, and you plot those against each other for thousands of supernovae across billions of light years. And you read off the history of how fast space itself has been expanding. That is how we know the acceleration is real. It is not a theoretical prediction. It is something we measured. And then we had to figure out what could possibly cause it. The first place people looked was Albert Einstein's old equations. When Einstein wrote down his field equations for general relativity back in 1915, he was troubled by the fact that his equations predicted a dynamic universe, one that was either expanding or contracting. At the time, the consensus was that the universe was static, eternal, unchanging. So Einstein introduced an extra term into his equations, kind of like adding a correction factor to hold things steady. He called it the cosmological constant, and he represented it with the Greek letter lambda. It was a kind of built-in repulsive energy spread uniformly through space, pushing outward against the attraction of gravity to keep everything in balance. Then in 1929, Edwin Hubble showed that galaxies are actually moving away from us, and the universe is expanding. Einstein dropped the cosmological constant. He reportedly called it his greatest blunder, which is a bit unfair to the idea, because it turns out the idea was not wrong. It was just unnecessary at the time. Now here we are, and lambda is back. The cosmological constant is the simplest mathematical way to account for the accelerating expansion. You put that term back in Einstein's equations, you choose the right value for it, and the equations describe exactly the universe we observe. So in one sense, the math is fine. The description works. But the description is not an explanation. Lambda is just a number. It tells you how much of this repulsive effect there is, but it does not tell you what the repulsive effect is made of or where it comes from. Sticking a constant into your equation is like saying the number of apples in the basket is 5 and never asking how they got there. Physicists do have a candidate explanation, and it comes from quantum mechanics. And it is simultaneously the most sensible and most embarrassing idea in all of physics. In quantum field theory, empty space is not actually empty. A vacuum is not nothing. It is a seething background of quantum fields, and those fields have energy even in their lowest state. Virtual particles are constantly flickering in and out of existence. The vacuum has what is called zero-point energy, and in principle, that vacuum energy should produce exactly the kind of repulsive pressure needed to drive the accelerating expansion. The structure of quantum mechanics essentially predicts that empty space should have energy, and that energy should push space apart. That prediction is right. The problem is the size of the prediction. When you do the actual calculation, you get a number for the vacuum energy that is somewhere between 60 and 120 orders of magnitude larger than what we actually observe. That is not a small rounding error. An order of magnitude is a factor of 10. 60 orders of magnitude means the theoretical value is 10 followed by 60 zeros times bigger than reality. This has been called the worst prediction in the history of physics. And I do not say that lightly. Physics has a long track record of good predictions. This one is spectacularly, historically, almost magnificently wrong. Something is canceling out almost all of that vacuum energy with extraordinary precision, leaving just the tiny residual that we observe. We do not know what. There is no known mechanism that could achieve this cancellation with such breathtaking accuracy. This is the cosmological constant problem, and it is one of the deepest unsolved problems in all of science. There are alternatives to the cosmological constant. Some physicists think the acceleration is not caused by a fixed energy of the vacuum, but by a dynamic field that changes over time and across space. They call it quintessence, which is a name borrowed from the ancient idea of a fifth element, though the physics behind it is entirely modern. A quintessence field is like a slow-rolling ball in a potential landscape, gradually releasing energy as it settles toward a minimum. This could explain the acceleration without requiring the extreme fine-tuning of the cosmological constant. But to test it, you need to measure whether the acceleration is truly constant over cosmic time or whether it changes even slightly. And doing that measurement at the required precision is pushing the absolute limits of what our telescopes can achieve. Another possibility is that the problem is not in our matter and energy accounting, but in our theory of gravity itself. General relativity has passed every test we have thrown at it in our solar system and in binary pulsars and in gravitational wave detections. But those are all relatively small scales and strong fields. On the scale of the entire observable universe, maybe gravity behaves differently. Maybe the equations need a modification at cosmological distances. This category of ideas goes by names like modified gravity or F of our gravity, and there are genuinely smart people working on them. The trouble is that every modification you make to general relativity tends to create other problems, and the equations get complicated very quickly. There is also a stranger possibility, which is that the universe is not perfectly uniform on the largest scales, and that we happen to live in an unusual region, a sort of cosmic bubble that has slightly different density from the average. If we are sitting in a local underdensity, the expansion might look faster from where we are than it actually is on average. This idea runs into trouble because the universe does look remarkably uniform when you average over large enough scales, but it cannot be entirely ruled out. Here is what makes this particularly strange. Dark energy, whatever it is, makes up about 68% of the total energy content of the universe. We cannot detect it directly. We cannot produce it in a laboratory. We cannot point to it. We inferred its existence from the motion of galaxies billions of light years away. Dark matter, which is a completely separate mystery, is another 27%. Ordinary matter, the stuff you and I are made of, the stars and planets and gas clouds, and everything we have ever directly detected is about 5% of the total. We live in a universe where we have a decent handle on less than 1/20th of everything that exists in it. The universe is mostly made of things we do not understand. That is not a comfortable place for physics to be, but it is an honest place. Now, there is something else that has been causing a lot of tension in cosmology recently, and it goes by the name the Hubble tension. Here is the issue. There are two ways to measure the current expansion rate of the universe, which is called the Hubble constant. One way is to look at the cosmic microwave background, which is the ancient light from about 380,000 years after the Big Bang, when the universe first cooled enough for atoms to form and light to travel freely. You analyze the patterns in that background radiation very carefully. You apply the standard cosmological model, and you get a prediction for what the current Hubble constant should be. The other way is to build that cosmic distance ladder using Cepheid variable stars and type I supernovae and measure the expansion rate directly from nearby galaxies. These two methods give different answers. Not a little different. Different enough that the gap is now considered statistically significant. The early universe measurement says the expansion should be a bit slower than what the direct measurements of nearby galaxies actually show. This disagreement is either a systematic error somewhere in the measurements, which would be deeply embarrassing but fixable, or it is a sign that the standard model of cosmology is missing something. Maybe dark energy is not constant. Maybe there was an early burst of energy before the cosmic microwave background that messed with the initial conditions. Maybe there is new physics hiding in the gap between those two numbers. That is the exciting possibility. A small discrepancy between two good measurements has historically been one of the most productive things in all of physics. It was discrepancies like this that led to quantum mechanics in the first place, when classical physics could not explain the spectrum of light from a hot object. What does all of this mean for the long-term fate of the universe if the acceleration continues, and if dark energy remains constant or grows? Then the universe is heading toward what cosmologists call the big freeze, or sometimes the heat death. Galaxies will eventually recede from each other so fast that they pass beyond each other's observable horizon. The night sky will go dark. Stars will burn out one by one over trillions of years. Black holes will eventually evaporate through a very slow quantum process. The universe will thin out toward a cold, dark, nearly empty state of maximum entropy. That is the current best guess for how the story ends, based on what we now know. Though given how many surprises this topic has already delivered, I would not put too much confidence in any single prediction. The thing that strikes me about all of this is not the strangeness of the answer. It is the strangeness of the question being answerable at all. We are tiny creatures on a small rock orbiting an average star in one of hundreds of billions of galaxies in a universe whose total energy content we do not understand. And yet we figured out that the expansion is accelerating. We did it by patiently watching old stellar explosions through large telescopes for years, measuring the color of ancient light and doing arithmetic. That seems almost more remarkable than the mystery itself. The universe is not obligated to be comprehensible, and yet it keeps giving us these hooks to grab onto, these patterns in the light, these gentle hints that if you look carefully enough and think hard enough, you can learn things about the largest structure of reality from a little blue planet at the edge of a completely unremarkable galaxy. The mystery is not solved. The tension in the data has not been resolved. Dark energy remains a label for our ignorance more than an explanation of it. But we know what we do not know. And that, believe it or not, is one of the hardest things in science to actually achieve.